Yes. Right, and he will give us a talk on a new acronym. So we've heard about the ADS, and we have a new acronym called the ADMSR, which he has coined for what is essentially a coupling of an ADS with a molten salt reactor. So this is an original concept which he's been developing at the University of Simón Bolívar in Venezuela. And Jean-Pierre needs to address some organizational matters beforehand.
Sorry to delay by 30 seconds the next speaker, but this is an important message for those of you who are going to a visit this afternoon. The schedule is very strict, so please follow the schedule. If your visit is at 16, then you have to be, at 16:15, you have to be there at 16 for those visiting Atlas at that time. Then there is another visit at 16:40. At 17, you have to be there at 16:45. It's because you have to get equipped. And the last one, CMS, for 17, you have to be there at 16:45. So remember your time, please. Thank you.
And don't hesitate to walk out anytime. It's, nobody will be offended. Right. Okay, you have the floor then.
Are you saying something about the title or no?
No, you can go straight ahead.
Thank you very much for the opportunity to give our talk. I would like to talk about the thorium target. I would like to present my colleagues, Dr. Bermudez, my PhD student, Felix Pino, my colleague, Professor Greaves, and myself. This is a collaboration between the National Nuclear Physics Laboratory in Leñaro and our university. Venezuela is a oil-producing country. We are producing around 3.7 million barrels per day. This means that from the energy point of view, we are independent. In the near future, if we would like to maintain this independence, evidently we have to look for other energy sources. An energy source could be the carbon, which is not very friendly, environmentally friendly, so we are talking about some minerals or uranium or thorium that could be used. The national program introduced the possibility to buy a nuclear power reactor from the Russian, and we signed already an agreement about that to use uranium, enriched uranium. In our point of view, our university is trying to convince the government to go forward the thorium. Thorium is quite available in our country. The reserve is quite high proved already. And it seems to me that we have to study further the possibility to introduce the energy for our future well-being, the thorium. This is why we are working in this field. I will talk about some general concept, but probably already heard about in these sections. Then I will talk about the possibility to use the aerosol accelerator, which is already in a design stage, coupled with the molten salt reactor, the Furukawa type. Then we are presenting some result of the modeling, some conclusions, and probably further works that can be done. In principle, there are two different kinds of production of energy, using mainly the rich energy in the type of the fission one, and then that could be used, or it is used already in the uranium cycle. Then you can look at the next philosophy, which is the spallation process, which is a neutron-rich in the sense that you are producing a step before the step of the fission, you have to produce neutrons. The spallation technique is one of the most useful, and what we are talking about here is the possibility to use this technique for thorium as a primary energy in a nuclear reactor. Really, what he has to tell about that the technology that actually is available is quite far away from the technology required for the second case. Already was mentioned about the story of the use of the thorium. I will just to mention that in the 1940s already the people thought about that one. As you know, if you discover something, immediately enter or for the health physics or probably to military applications. And in this case, immediately the thorium was considered for it. Then later, there was made some experience, as already was mentioned, the molten salt experiment demonstrated the feasibility, even if it was a few years after completely suspended, and today we have to reintroduce our knowledge and our discovery of the technology required for this technique. Then, in 1994, the Nobel Prize winner Carlo Rubbia proposed this energy multiplier that we already heard quite a few times in this talk. This energy multiplier is also called as a Rubbiatron, and as was said also here, that our meeting mainly due to also to the initiative of Carlo Rubbia. Then what we are thinking about, how it will be the possibility to use this thorium. The first step will be, sorry about that, I am not keen about this one. Well, come on, come back to the first one, that's it. Okay, the first stage in this case will be to make a prototype or something similar to a molten salt reactor in which the energy will be quite low, but certainly will be useful to gain some technological information. It will be possible to build it in the next few years if we start, let's say, today. Evidently, the cost of this first prototype is exactly the equivalent of 1 day production of oil in Venezuela, which means that from the economical point of view it will be done, but unfortunately the political decision does not agree quite well with this idea. Then, once we could gain some information or some technological advantages on this prototype, it could be further extended to make another power supply of nuclear power reactor around 300 megawatt. This demonstration reactor could be built around 10 years. Evidently, in this case, we should use some enrichment uranium and could be used as a thorium breeder too. The next step in our imagination, let's say, is related to the possibility to defund such a kind of different type of reactor using the thorium fuel around the world in such a way that we could somehow gain sufficient gain about the use of the stockpile existing in uranium-235 and the plutonium-239. Naturally, this kind of possibility will take a larger time, several tens of years from the start. Then the fourth stage will be related to what we are talking about, the accelerator-driven molten salt reactor. This could be used, one of the devices that could be used for actinide and destruction and uranium-233 production. The time scale would be much larger and is related to the Furukawa concept, who developed this technique in his details. What will be the last stage? Last stage would be related to a regional center in which several of those units could be used both for the destruction of the actinide or the spent fuel in nuclear reactors existing today, and evidently to be able to produce further fuels and have the advantage of producing also energy. So in this case, we would have a molten salt fuel cycle, and it can be used as a destructor of this spent fuel. So there will be two advantages of it. Naturally, this one would require quite a lot of energy and study, but certainly it could be one of the schemes that we could follow. What are we proposing here in this case is to use the aerosol accelerator. As you know, there is already developed a target in which the spallation source is obtained by impinging high energy protons and high current on mercury. This one will produce a large amount of neutrons, and acting on the target of the uranium, produce exotic nuclei beams, which means that this geometry is already well studied. And what we are proposing is trying to reproduce with the same geometry the possibility to be used in the ThE fuel for a nuclear reactor. This is the main idea. You can see here the accelerator itself. This will be the target at which we are interested, and this will be the usual cycle for heat removal and the removal of possible fragments of nuclear fragments, fission fragments. Here, again, there is a system complete in which the fuel, in this case, the ThE, has this composition. This naturally one of the tools possible, but will be operated around 550 and 700 degrees. What will happen then that this 1 JeV and 1 milliampere beam, proton beam, will impinge on this center, produce the large number of neutrons, which will be absorbed by the ThE plus thorium and uranium target, and will produce not only energy, but it will produce also the transmutation of the thorium. Then this will flow through a heat exchanger and go back to a center where the chemical processing has to be included, and then from there, if you established all the fuel and you controlled that the specification of the molten salt fuel did not change, or if it changed, you have to reestablish, then it goes again at the center to receive the further irradiation and recycling again. This will be the general concept what we are talking about, and our interest will be exactly on the target design or to learn about the target. The FLUCA modeling will require the geometry simplified as it here. This is the case in which the ThE will go inside, will receive the radiation, and then come out. And will be surrounded again of the ThE fuel in such a way that can be and somehow larger production of thorium transformed in uranium-233 or transforming the actinide. So in this case, we are interested in see what kind of information we can get from such a similar type of target at the FLUCA with evidently different material. Here is the Hastelloy, and was mentioned several times, but we have to stress that if the composition is changing due to the neutron radiation, then the Hastelloy will respond differently. So the most important thing is the chemical processing plant, and it was mentioned that this is a typical interdisciplinary science, and certainly it is, because involved with the accelerator technology, the reactor engineering, and most of all the chemistry that has to be taken into account. What will be the parameters? We already mentioned about the beam energy, then the beam diameter, which is changing because we have the shape as we already saw in the geometry of aerosol. The target will be a ThE with thorium and uranium, and the reactor will be an aerosol accelerator-driven molten salt reactor using the specification given by Furukawa. Here again, I am just showing what I did, showing the details of the target made by SAMEC. This is available on the internet side, and you will see that this one is the place, the window in which I was telling you the diameter is 7 centimeters, but here in the center there is a small window which is 1.6 centimeters. The ThE will flow inside, receive the radiation, and from the coaxial tube it will flow out. This is just to show you what we think should be the target. Then, to run the FLUCA model, we need some data. The most important is the geometry. You can see here that is the central part we already saw. This is the impinging proton. Then, from the outside, you will see the ThE, then contained in graphite, and outside we agreed with the previously spoken topics in which the nuclear reactor absolutely has to have a containment. And this is why we are introducing here the concrete. The data, you can see it here, what will be the values that will be introduced in the modeling. And then what we are expecting from as a result from the modeling is the isotope produced per milliamp evident of the accelerator, neutron spectra, because this is the most important thing for the reaction rate that we are looking for, and the neutron fluence, the energy, the density of the energy of the place produced, and the fission density. The fission density will tell us how to remove or how fast we have to remove the fission products. This is the result that we get from the Fluka run. You will see that here inside there is different colors, and the colors means how fast is changing the density of the fluence of the neutrons inside. It is expected exactly here outside of the center, and this is probably because the proton will have some degrading during the entrance of the window. In this window here, you will see around here is the graphite, this is the proton beam, and this is inside the flip that should flow. Here in this particular case, we use one system without any flowing of the fuel. Then the other information that we get here is the energy density. Again, you will see that the energy is quite uniformly distributed in the center and degrading very fast until to very small values. This one is the section cut exactly in this way. So once again to show what will be the energy deposited inside this kind of target. Fluka result give also some information about the fission density. As expected, again, it will be very high in the center, degrading going to radially outside. And then here is the graphite in which you are not expecting any fission fragments, evidently, because the fuel is not there. Then we will have some results. This result will guide us to see how good is our approximation, or what could be the next step for further studies. So we have here the type of material, which is inside the volume or the outside. There are different values that we have observed. This is for the data for the target studied. In this case, in the below, we are using it in function of the volume unit, in such a way that you can probably have a larger scale of this target. In the case you will have to remove farther or faster the energy produced. Then, as mentioned earlier, the most important things in this case is to see the fission products. The fission products, in this case, we will have the distribution that we already know. And then we will have here the actinide captured by the neutrons. And here is how the FLIBE will be alterating due to the neutron absorption. So the internal volume is this case, and this is what we are looking, or what will be supposedly to have inside the entering of the FLIBE inside the target. So the proton will immediately interact in this zone, then move around here and coming out. Let's see what will happen in the outside of this result. So in this case, you will have the FLIBE region, and you will see again that the result does not change much, but certainly there is a slight difference between the two cases, mainly due to the larger quantity of the fuel is outside, but is in a moving way, so it is expected that it will be lower the fission, higher the fission fragment than inside here, where the neutrons is higher. Let's see now some neutron spectra. Neutron spectra, as mentioned earlier, is very important to have information about the reaction rate. So the structure that you will see here is evidently a representative about what will be happening in the material and how fast or with what frequency you will observe it. This is the neutrons produced in total, 2 per 10 to the 8, and here is the neutron fluence in the external pad is a factor of 10 higher. Neutron spectrum will change because the FLIBE inside is changing with time, and also because this component is quite different. So we have to have some idea about what's happening. The idea that we had is that the graphite, also the internal and the external, will contribute to modify the spectrum and also to increase in the center, because it's the reflection of number of neutrons that is very important in this case. Then, since there is a leakage, evidently we will have some neutrons inside this containment. The containment of concrete will absorb some neutrons, and you will see that the shape is slightly quite different than what we saw above, and is changing also its fluence. Well, this is what we have so far about this study. The question is what we can conclude about this one. The first conclusion is that all the study made for the aerosol, it could be used in the case for to be used as an accelerator driven molten salt reactor. The next question is, can this reactor be a power device or a fuel breeder or a actinium-based burner? To answer this question, we should go a little bit further. Carlo Rubbia already was mentioned to propose this system, and it rises the opinion of the Scientific and Technical Committee of the CERN, in which they state that probably the energy multiplier would be a fuel breeder and actinium-based burner. In this case, the answer will be that also in our case, our result will show that the opinion of the CERN Scientific Committee is correct, or it's approved. What shall we do in the next step? Make some fluid transport modeling and see the delayed neutron effect. As you know, the fuel is moving around in the secondary, in the first circuit before it's exchanging the energy, and is producing neutrons. The neutrons usually, the delayed neutrons usually is one of the ways to regulate the energy produced inside the system. Then we have to improve the numerical solution, evidently, and also to see what will be the extension of the fuel degradation on the effect of the whole nuclear system. Thank you for your attention.
All right, thank you for this talk. Are there any questions? Yes.
You are using the free bed as a spallation target, or equivalent of a spallation target. So how does it compare with lead in terms of the number of neutrons, primary neutrons that are produced?
Thank you very much for your question. It's very interesting. Usually, I was told to use lead, bismuth, correctly, you are right. But since I mentioned that we are interested in the same system that we use in aerosol, because we already have some results, we wanted just to use the FLIBE only to see what would be the outcome. So certainly you're right. In the very first time we used mercury, but the mercury could not be used because the temperature is very high. So the result that we obtained was an academic exercise. Then we used the FLIBE. So it seems to me that by comparison, the FLIBE should be used only because you can use it as a fuel and as a cooler immediately. In the case of the lead, you have to introduce another cooler, which means that you make it a little bit complicated. In our philosophy, we thought that it will be simplified.
How does the number of neutrons produced in FLIBE compare with that in lead?
Oh, you mean the spallation?
Yeah.
Well,
the
source
source
much higher in the lead. Sure, certainly, it's much higher in the lead. Because in this case, the spallation will be mainly in the heavy elements, the thorium and uranium, which inside, which is a lower density. It was around 2 point something, the density is low. The lead is almost 11, very high. So it means that from the efficiency point of view to produce neutrons, evidently the lead is much better. But you have to take into account the complexity that you are taking into account in the case of the lead.
Yes, Hamid, you have questions.
In the beginning of your presentation, you said that the 10 megawatt facility, you could make it within the 5 years if there is a will to do it. have you taken in this assumption the licensing? Because I think, I mean, from the technical, if we are in our lab, we can do everything what we want, if we have the money and we can do it. But, I mean, when it comes to a nuclear reactor, we have to take this licensing with us. And I think I can tell you, a 0 megawatt ADS LED that we built it in 12 months. But to do the licensing, it took us 5 years. And this is zero power.
You are absolutely right. I accept your point of view, and I mentioned that we are an oil-producing country, not a nuclear country. So if you ask me if I will be able to build this reactor, I am certainly not. Alone, I will not be able to do. And for the licensing, certainly it will be much, much longer than 5 years as it expected. I am reporting this because Professor Furukawa, who did come to visit us, was able to produce this kind of time in the time interval. So I am reporting what he said. In our case, absolutely not. Thank you.
Right.
I have a small question,
Just
please.
one last.
I noticed the frequency.
Okay.
Should stand up. I noticed for the frequencies of your accelerators that you used for the injector and for the high energy part, the European frequencies. But for the middle part, the, let's say, Japanese-American frequencies, or American-Japanese, whatever, who did it first, that can somehow does no longer fulfill the harmonics conditions. Is that just a misprint, or is there some very special things which did escape to my understanding?
Well, I would not mention anything about the accelerator because I am concerned only this point.
But you should.
They told me that is 1 JV and.
I accept that, but you should say to the colleagues, if it's 176 and 704, it cannot be 325. Then it must be 352. Maybe it's just a misprint.
It's a mistake, yes.